Hey, good afternoon, everyone. So today we're going to talk about real-time data lineage at UBS. I'm Sid, and we have Wren with me. We are the two tech leads on an application that we built at UBS to generate lineage, capture all the metadata to generate lineage, and we'll walk you through our use case. You know, let's start. Um, so what's on the agenda, right? We're going to start with data lineage and data governance. This will give you an overview of why or what our requirements were and how we implemented them. Then we'll move into group data dictionary. Group data dictionary is an application that we built in the ref data space to capture all of this metadata and generate lineage. Next we'll move on to the Neo4j sync. Then lineage generation, which is the meat of all the data analysis that we're doing. And finally, we'll talk about what we learned from this project, what enhancements we need to make going in the future. So what is data lineage? So data lineage allows us to track the origins of data. It helps us understand the data lifecycle, and it helps us to analyze how data moving through an organization impacts the organization, how changes to data impact that organization. And why do we need data lineage? So as I already said, data lineage allows us to track data as it flows through an organization. So in the small example that we have over here, you can easily see how all the data is flowing through different applications in organizations. It allows us to track errors that happen in data quality. So for example, in this case, you can if there's an error in one of the attributes in an application, you can easily understand what all applications is it going to impact. This makes it easier to to fix the error and not impact and to understand the impact at least. It also allows us to track what happens when data changes in one application, right? So in our example again, if the application 3, the attribute is changed, we can easily see that it's going to impact another application and how it's going to impact another application. In this use case, it's very simplified, but imagine an application that's serving 20 upstream users, or maybe 100 upstream users with attributes impacting multiple users. This sort of information will make it very easy for them to say with confidence, is a change in an attribute a big impact on the flow of data, or is it not, and how careful they must be about it. Moving on to our inspiration, or like why we needed to build a data lineage system. This was basically driven by BCBS 239. BCBS 239 is the Basel Committee on Banking Supervision's regulation to help improve all the bank's risk data aggregation capabilities and to improve the bank's reporting practices. They enforce certain standards to help achieve this. So they want to enforce improving the accuracy and integrity of the data, the completeness of the data, to make sure that all the reports that we generate take into account all the risk factors, not just they don't miss anything. The timeliness basically says that the risk reports or any reports should be generated on time, and all the data should be up to date. And the integrity, which is just the correctness of data. I mean, the risk report needs to have the correct data backing it for it to be effective. So this is the application that we built. This is, we call it the Group Data Dictionary. It is a data governance platform. It's a lineage generation tool, and we can run a lot of reports on it as well. So it takes into account all the assets that we need to govern. It has a workflow to allow users to input all the data, and it allows us to, and the workflow basically makes sure that all the data in there is correct. It goes through a 4i check to ensure data quality. We have audit capabilities to make sure that we can go back in time and understand what changed when, who changed it, and other things that go with it. All the changes that are done in this application are basically approved by SMEs to make sure we always add the correct data in the application. And this is ultimately what's powering the lineage that we generate. The data needs to be correct for the lineage to work. It has lineage generation capabilities also. So we use Neo4j over here to generate lineage. So once all this data is ingested, we use Neo4j to evaluate the lineage, and we get a response in graph JSON. That graph JSON is then fed into a D3 visualizer to basically see the lineage, and that's the lineage generation capabilities. Again, it helps us to answer all the questions that we talked about previously. It helps us understand the flow of data through the organization. It helps us understand how changes in one application are going to impact the entire organization. It helps us understand how errors can propagate through the system. And finally, we have the reporting. So now, once we have all the metadata in one location, and we can say with some confidence that it's correct, we can do a lot of reporting on that. So we allow ad hoc reporting, and we allow exporting the entire lineage as an Excel as well. This also, with the ad hoc reporting, you can get insight on what data you need, or you can get insight on the data, on the go as well. So the first iteration of GDD, it was built on Oracle, and the lineage generation was also in Oracle. We shifted from Oracle, or we decided to shift from Oracle to Neo4j, and the main reason for that is that the lineage data is highly connected data, and it's more naturally persisted in a graph database like Neo4j. And also traversing this connected data becomes much easier in Neo4j. In PL SQL, it takes joins across multiple tables to generate the lineage. And then once you have all this data in a relational format, you have to add a processing layer to format this into an object, and then visualize it. With Neo4j, Cypher makes it easy to traverse this connected data, to traverse this graph, and it also makes it easier to visualize it. So this is the reason that we're moving to Neo4j. So Group Data Dictionary, that is basically a data governance tool also. There's no official model for data governance, but because every organization has a lot of different data, and then they operate in a different way. But looking online, we found this one model which is distributed by Colibra, which is a data governance platform. It says that data governance can be divided into 3 categories. It has the asset model, which is the what of the data. It says what needs to be governed. Then we have the execution model, which talks about how the data is governed. It talks about validation rules on the data. And then we have the stewardship model, which controls the who of the data governance, and it controls who makes these changes, and to control the quality of data. So we'll move on into the asset model. The asset model is where lineage exists for the most part, and this is also what GDD, or Group Data Dictionary, deals with. So as you go up the asset model, you move into more of a conceptual realm, and as you move down the asset model, you move into the physical realm of actual data attributes. GDD lies, the scope of the Group Data Dictionary exists in the top half of the asset model, mainly in the enterprise data model. So within the reference data IT space, we've implemented a data distribution platform that is similar to Group Data Dictionary previously also, but it resides in the physical part of the asset model, on the lower parts of the asset model. One of the future directions that we want to do over here is we want to use the physical model to understand data as it flows from one consuming application to the other. The GDD right now is based on the top-down asset model, but an early iteration, the first version that we made, was actually based on a bottom-up model, bottom-up asset model. So moving on to what our Metamodel looks like, and tying it back to the actual data governance model. We have all The assets in orange, this is basically everything that's used to generate lineages. We have applications, which are basically systems through which the data flows. We have concepts. Concepts are basically conceptual or aggregations of physical data. So, for example, a car comes together when you put together physical stuff like a steering wheel, a wheel, or an engine. All of these together form the concept of a car, and that's what a concept is. And then we have elements, which is the actual physical data. Having this concept helps us answer questions like, how is all this data aggregated? So in going back to our example, what we can understand from this is, how are all the attributes that make a car or make a concept, how do they come from? How do they flow through the entire organization and come together to form this one concept? So we have data flows also. These data flows basically show the flow of data between applications. They are configurable enough in our case to actually show creation of data in a certain application. So you can denote that an attribute or a concept flows from one application to the other, or it gets created in one through these data flows. And that's the asset model in our data model. Moving on, we have the controls and the principles. These are the validations that need to be added or that are performed on the data. This is the monitoring, basically. Apart from this, we have certain roles for all users. Specific users have permissions to edit data. Specific users must approve data or approve the changes for these changes to be accepted, and that controls the who of data governance, or who makes these changes, or who controls the changes. All right. So as we talked previously, so our first iteration of the application actually used Oracle to generate lineages. Moving on to Neo4j, we still wanted to keep Oracle because all of our workflows were integrated with Oracle. All of our audit capabilities are integrated with Oracle, and Neo4j didn't have a proven concept of audit at that time. So we kept Oracle, and we decided to synchronize Neo4j with our Oracle database, and we did it in 3 steps. So we started with a full-time sync, which is basically we create the entire database from scratch. So you have inserts that create which read Oracle and create the entire graph database. Then we moved on to the real-time sync, and this is basically to propagate any changes that happen in Oracle in real time or near real time into Neo4j. And finally, once these were done, because we're skeptics, we created a reconciler to make sure that all that these databases are actually in sync. So let's go into the full-time sync or the full synchronization. So we started with creating procedures in APOC for each table that we have in Oracle to create 2 inserts. Once these procedures were done, we run these procedures in a specified order. So first we create all the assets. This is the chunk of the data that's governed by GDD. Then we create the data flows and link all of these assets together, and this is what basically creates shows how data flows in from one application to the other in Neo4j. And finally, we link all of these assets together. So we link controls and applications to show what controls an application performs to make sure that the data quality is maintained. And all these queries run in a sequence, and this is how the full sync is done. Then we started to look in the incremental sync. So we first looked at the Neo4j blog, and there was a use case by Monsanto where they synced Oracle Exadata with the Neo4j, and they used Golden Gate and Kafka for that. This use case makes a lot of sense. For Monsanto, they had very high volumes, and they needed to add some extra technology in their tech stack to make sure that the sync worked fine. For our use case, Group Data Dictionary it's a metadata repository, so we didn't really have a lot of volume, and it didn't really justify adding all of this additional technical complexity to synchronize them. So we ended up using, we ended up keeping it simple, and we created a queue in Oracle using an Oracle table. So every time a user interacts with our application and they issue changes into the Oracle database, we have triggers on each table that create or that log all the changes in a transaction table. Our synchronization application reads from this transaction table effectively as a queue, and it reads each transaction one at a time, and it tries to sync. It persists those transactions into Neo4j using APOC and Java. So for this, we actually had to write, not just create. We had to do inserts, updates, and deletes. And we had to do this for each of the tables in Oracle. So any change that happens in Oracle gets logged into the transaction table, and then it's read from the transaction table and synced into Neo4j. And that's how we achieved our incremental sync, or almost real-time sync. After that, we moved into the reconciler, which is a simple Java app. It connects to both Oracle and Neo4j, and it counts the number of assets in both these databases. Make sure the counts match. We make sure that the IDs match. This ensures that these databases are actually in sync. So we'll move on into our architecture was simple enough, but we did have a lot of challenges. Implementing it and getting it to work, and ironing out all the wrinkles. So since all our assets go through a workflow, all of these assets are in a different state. So if they're approved by SMEs, they're in a published state. But if they're in the middle of a workflow, then they can have different states. And what we needed to do was we needed to provide the users a view of the latest data, which doesn't care about what state the asset is. And then we needed to provide our users a view of the data in the published phase. So this, for example, over here, we see that all of these, we have the attributes in application 3 in draft phase, but everything else is published. So this is the latest view of the data that we have. But sometimes for reporting purposes, we need to provide the latest data. We need to only provide information that we're sure is correct. And in that case, we would generate a lineage which would look something like this, which would only display assets that have been published, that have been reviewed by SMEs. The second ingestion challenge was unpublished assets and rollback. So there, in a lot of cases, if there's deletions on assets that have never been published before, or that have never been reviewed, somebody added incorrect data and they had to delete the asset, for example, even though it's linked, all changes in Oracle, we had to, we didn't just have to delete the asset, we had to delete the relationships as well. So we had to do a little bit more maintenance than we actually, a few more steps of maintenance. And the way we achieved this latest versus published view is we created different namespaces for each of them. And with each namespace, we run the same queries to get the lineage, to generate the lineage. So that simplifies the lineage generation part. It just adds a little bit of additional complexity to maintain the two namespaces. So in this case now, we would have to make corresponding changes, and not just one, in both the namespaces. So I think that's all we have for the data ingestion and what GDD is. I think we'll have Wren here to talk about Lineage. All right.
All right. All right, so now we're moving on to the lineage generation. As noted previously, lineage is used in the context of data governance to make sense of data that's processed by the firm. Here's an example of a lineage diagram that covers descent and title succession within the UK. And in this example, titles and houses are mapped to data concepts that Sid mentioned earlier. People are mapped to applications. I'll get back to this diagram later, but this gives you a more concrete example of what a lineage diagram would look like, applicable way of doing it. So we have 4 types of lineage generation algorithms that we created. I'll go over it, this on a high level, but I'll dive into it in subsequent slides. L1 is the initial algorithm that we developed through PLSQL with the performance optimized to 40 seconds. There was a Cypher variant that was created during the initial development, but it was shelved because we couldn't get the real-time synchronization to work that Sid covered, and it couldn't handle the draft namespace. In the upcoming release, the plan is to deprecate L1 in favor of L2. L2 is the new algorithm that we developed that's effectively the same as L1, but it's based on the new data model. It's currently, the performance for it is 30 seconds, but it's not optimized yet. L3 is a variant of L2, with boundary intersection being factored into the mix. A boundary is our way to designate how applicable concept or element is for a data flow. I will cover boundary intersection in a later slide, but you can think of it as we're putting an accumulator along a path, and using the accumulated results, we figure out whether to factor in or out edge. L4 is a variant of L1 with a metric, which is a special type of concept that Sid mentioned earlier. It ties back to the BS 239 regulation because it's a special report that tells us how the firm checks its risk. So it's currently implemented on top of L1, but we have the intention to migrate it over to L4, the Neo4j. Note that L4 is effectively a subgraph of L1. So in theory, we could actually use L1 as a pre-processing step and just filter on top of that. We do run another Cypher query on top of L1. So this is how the algorithm for L1 and L2 is actually broken down. We initialize the filters where we're starting. The applications is mandatory and concept is optional. We can drill down further to specify, I want a specific concept to be used as a filter for this given application. And we traverse both in the upstream and downstream direction through the data flows that flow in and out of the application. Data creation can happen within an application. That's when an application takes some input data concepts and transform them to something else. We iterate this through breadth first until there's no more new edges found. At the very end, all the paths that we find, we compose them into a graph JSON representation. So this is the algorithm kind of visualized. We start in the data distribution app, right, in yellow. And on the first iteration, we go through the red concepts, and the paths that are colored in red are where we iterate through. On the second iteration, we go to the ones in blue. You can see in the risk calculation app that risk is calculated from price and rating data. And eventually, it goes to the reporting app, and you can see that the metric, value at risk here, which is a report provided to the regulators, is generated by two of the concepts here. The third one is not included because we didn't start, the data distribution application doesn't share the concept to this metric. The boundary intersection for L3 is complicated. It's a condition set that we kind of apply on the metadata for a concept. It's broken down where you have an expression, key equals value. The example would be country equals UK, division equals IB, asset class is equity. And then you have expression sets, which is you compose these expressions with an AND operator. And you have boundaries that are composed of multiple expression sets. The evaluation of boundaries intersection is effectively a cross product of all the boundaries involved. And you can think of it as effectively Boolean algebra between all the expressions. Like I said before, boundaries accumulate along a path, and if there's no intersections, the edge is not included. Going back to the example I had about the title and descent lineage diagram I showed before, this is the title and descent for the UK. And if you use Queen Elizabeth, I guess, as the starting point, and you trace only the patrilineal descent, you go back to the earliest recorded founder of her line, up to her parent house. But you wouldn't have Prince Charles in that line, the blue line. That's because gender, in this case, is the boundary condition. We're just tracing it through the male line. Then if you use Prince Charles as the starting application, you go up the red line. Here's an example of like the intersection that happens. I'm not really sure how visible that is, but if you look a little deeper into it, the boundaries get more restrictive as you do across products. So eventually, there's a point where a path is no longer viable. This is an example of when a path is no longer viable. There are no further intersections, so we don't proceed down the associated path. As noted, boundaries intersections are applied additively, so the boundaries will become more restrictive with each hop. So some of the challenges that we're facing with lineages is circularity. We have to avoid walking over an edge twice. The default behavior is relationship global. It's when a relationship cannot be traversed more than once. We opted for a relationship path. Unfortunately, it means that it will impact our performance, but we'll have to do some optimization, like memoization, to make it work. Then there's the complexity. Our original decision to use Neo4j is because we wanted the BAs to be able to translate business requirement about lineages into something that the developers can use to do development. But the current implementation relies heavily on APOC and Java. It helps make unit testing easier, but it makes it less readable and maintainable. We're working on improving this with the help of Neo4j. There is a lot of coupling at the moment with the data model, because we coupled the current data model in Neo4j with Oracle and the presentation layer, because the presentation layer is effectively another graph. This makes it so that we have to massage the data in order to make it our algorithm work. Another challenge that we face when evaluating some tools and libraries that we could potentially use is because there isn't really a standard for a graph format. The example I show here is actually a graph JSON. It's one provided by Alchemy.js. There are other JSON formats that are similar in structure. Like Neo4j provides an output that switches the edges to relationships if you pass an option in your Cypher query. And there's also an XML equivalent of everything, all the JSON formats as shown before. It appears that they exist before the JSON formats. And GraphML is one of the more popular ones that is supported by Neo4j as an output. Some of the enhancements that we're considering is we want to reduce the coupling with the presentation layer. We could rely on graph transformation to create the final lineage diagram, but it adds an additional level of complexity, because graph transformation is a complicated problem. There's actually a series of conferences. I think that this year in July, there was a graph transformation conference that happened, and one of the tools that came out of that conference is something called the Graph Rewriting and Persistence Engine, GRAPE, which is something in Clojure that you can actually run on top of Neo4j to do graph transformation. We're also considering leveraging APOC procedure that creates virtual nodes, relationships, and graphs. It appears that the APOC procedure might be closer to what we want, but again, we do have to write out the logic of what our transformation entails. To reduce the complexity of the algorithm, we're considering using a more expressive graph traversal language like Tinkerbot, Gremlin. There's a library that exists already, but we haven't gotten to work yet. And I believe it's because Neo4j moved from 2.x to 3.x, and Tinkerbot is the same thing. They're up to 3.x. The existing Neo4j plugin doesn't appear to be compatible with Neo4j 3.x, so this route might not be as feasible. With the native graph platform that Neo4j is coming out with, and maybe the Spark, whatever they mentioned in the keynote, we can probably use that as well for enhancing our diagrams. In conclusion, there are some lessons that learned while we were making this change. Moving from relational to a graph point of view is really hard. It's tough on our developers and BAs to understand the functionalities and limitations of graph database because we're so used to the relational world. And within UBS, since we have to audit everything, relational makes much more sense with us. We're Oracle shop. Translating the user requirement is also challenging because in order to do graph properly, you need to apply the appropriate constraints on it because most of the graph algorithms have an NP-complete nature. If you remove the constraints, it means that your algorithms can't complete in polynomial time. One of the difficulties we have is ensuring that we have all the test case. There's enough coverage. There's no tools for doing it really easily. Like Java, you have code coverage plugins that allows us that tells us how many branches, how many lines has been covered. We don't have that with Neo4j. GDD is still a work in progress, so I think this is the end of the slides. If you have any suggestions or any comments that you can talk to us in the Q&A. I think that's it. Thank you.